These are the notes for section 2.6, graphing of basic functions. So this is just sort of an introduction to some more complicated graphs that we're going to do in the next couple of sections. First, let's talk about the topic of continuity. So you can see the word in there, continue, kind of continuous. So a function is continuous over the interval of its domain if it can be drawn over that interval without lifting the pencil from the paper. So if you can take and draw the whole graph, so remember these have arrows on the end because they go to the end. If I can take and draw the whole thing without lifting my pencil, then it's continuous on that particular interval. So what we want to do here is answer the question as to over what interval are these graphs continuous. So these graphs go on forever. So this first one, A, and so it's going to be for everything, for all natural, for all real numbers from negative infinity to infinity, this parabola is going to be continuous. So if we look at B, this one is something that probably we've never seen before, and it's got what we call a hole. So the function, of course, goes off because it goes off the edge. So remember, our rule in this class is that if I give you a graph where the curve hits the edge, we're going to assume it continues. All right, so this thing ends. So we have this little thick, it looks like a big dot, but that's hollow in the middle. So that is our designation for a hole. So that point, in other words, if this was a function, say f of x, and I said, what is f of negative 2? You would say it's undefined. I don't have a value for f of negative 2. So this function is continuous from negative infinity all the way up to negative 2. So we have negative infinity up to negative 2. And then on the other side of the hole, it continues. So from negative 2 up to infinity, it is continuous. So that hole, sort of that point there, has been removed. There's a hole in our function. All right. Now these next ones are starting to look a little bit like something we're going to see on the back of the sheet called a piecewise function. So a particular function applies for this part, and then for this part, and this part, and this part. But ultimately, I could draw the whole thing without lifting my pencil. So let me add some arrows on the end. You should probably do the same. So this thing is different. It's got different functions for the different regions, but it's continuous over everything. So negative infinity to infinity is the region in which it is continuous. All right, and then this next one. So again, this is a line, and this is some kind of parabola function. It looks like quadratic, perhaps. And so we start at negative infinity up to this point. So we have negative infinity up to positive 1 inclusive. It's continuous up to that point. Then I would have to lift my pencil, come down here, and just go on the right side of that dot, and then continue. So that will be 1 to infinity. Now, notice this one is a hole, meaning this endpoint doesn't exist down here. Instead, it's up here. I notice if both of those were solid dots, then this would not be a function. The vertical line test would fail at an x value of 1. So when you get things like this, one's going to be closed typically, and one's going to be open. I suppose in theory they could both be open up here and down here, and then the function is not defined in that case at a value of 1. So if I asked in this case, what is f of 1, then, gosh, I guess that's probably 1, 2, 3 and a half. So that would be, 7 halves. F of 1 is 7 halves. Not down here at what looks to be about a half, but it's this one up here because that's solid. That one's open. Okay, we'll talk more about this when we get to piecewise functions. All right, so let's graph a couple of functions. If you want, you can certainly use Desmos to help you graph some of these. This one is called, well, I mean, you can think about just making a table, but in your head, if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2, and so on, right? And then -1 is -1. -2x gives you -2y, and so on. So that's this function here. And this function it's going through all those corners, has a name called the identity function, because the x and the y values are identical. So this is going to come into play. This identity function is going to be useful in future lessons. Okay, so identity function. This is simply an easy sort of quadratic. So if x is 0, y is 0. If x is 1, y is 1. And if it's -1, it's also 1. If x is 2, then y is 4. 1, 2, 3, 4. And we'll stop there because if I go to x is 3, it would be 9, so it would be off our graph. So let's sketch that one in. So that is one of our quadratics. The graph is the shape of a parabola. All right, and this one's a cubic. And again, if we just simply do 0, x is 0, y is 0. If x is 1, y is 1. If x is 2, then y is 8, because 2 cubed is 8. Now, it's not mirrored over here like this one is. Instead, if I do -1, that is -1, because -1 cubed is -1. And if I do -2, then that's -8. All right, so that's a cubic function. Let's see if I can draw that one in. It kind of flattens out a little bit and then goes steep again. Okay, so something like that. This one's called a cubic. Cubic. This one's a quadratic. And sometimes referred to as a parabola. And this one's the identity. Identity function. Okay. All right. So now let's graph a couple more. Again, if you wanted to go and look at these in Desmos, but what I'm going to do is just kind of think of some x values. I'm going to sort of make a table. Oh, sorry, we were supposed to say what the domains are. So the domain here is -infinity to infinity for the identity function. The range, -infinity to infinity. All right. The domain for this one, it's going to keep going and go further out in the x direction. So it's all real numbers. There's no limit as to what x value can take on, but there is a limit to what the y values can take on for this particular function. Not all quadratics, but for this one, we can go down. Oh, we can be on a value of 0. The lowest value is 0. And it actually takes on a value of 0, so it's a closed bracket, and then up to infinity. Okay, this one acts sort of like a line. It keeps going. You can put any x value in you want, so there's no limit in the x value. So that's -infinity to infinity, and the range it can go up as high and low as you want. So also all real numbers, -infinity to +infinity. Okay. All right, now let's look at number 4. This one is a square root function, or a radical function. Sometimes we refer to them as radical. So square root or radical. So let's put in some values. So x is 0, y is 0. If x is 1, square root of 1 is 1. And then, like, let's not put in 2. That's not a good value to put into a square root, or 2 or 3. But 4 would be good. So put in square root of 4. That gives us a 2. All right, and so you can kind of see this is a sideways parabola. Now, what about if I put in -1? Well, I can't, right? So I can't put in anything lower than 0 in this case. That radicand, that thing in the square root, cannot be negative. So that means our domain is going to be, well, not parentheses. The domain will be 0 to infinity. Now, we just plugged points in that were nice so that we could do square roots easily enough, but you could certainly put in, a 3, a 5, a 6, a 7, you could put in lots of different values there. They just won't be nice whole numbers. So we picked the ones that were nice whole numbers. Notice this is sort of like a sideways parabola, except we don't have the bottom half of the parabola. Because we really want to think of this almost as a function. And so we don't have the bottom half of that parabola, okay? And so the range, the lowest value for the y is 0, and then that also goes to infinity, okay? All right, cube root of the function. So think about this. What would be the cube root of 0? 0. What would be the cube root of 1? 1. All right, and then what other value would be? I mean, we could put 2 in, but the cube root of 2, that's hard to do. So let's find a perfect cube. So if I go 8, cube root of 8, then that will be 2. And then -1 is cube root of -1 is -1. Cube root of -8 is -2. All right, and so you can see this should kind of look familiar. It has a very similar shape as this one up here, the cube. So we'll talk about that more when we get to inverse functions. But yeah, those are very related functions. They look very much the same, okay? All right, and then this last one is the absolute value function. So again, 0, absolute value of 0, 0, 1, 2, 3, 4, right? So it looks a lot like the identity function when x is positive, but when x is negative, -1, the absolute value is 1. Absolute value of -2 is +2, and so on. So this looks, let me sketch this in. Looks like the negative identity when x is negative, but positive identity when x is positive. All right. Let's go back and do this domain. Sorry, I skipped it on number 5. You can see this. I can put in any x value I want for this. We, again, put in nice ones that were easy to take cube roots, but ultimately it's a continuous function, so it can be any real number. And the range, same thing. Negative infinity to infinity. All right. And then here, x can be any value. You can put in any value you want, all real numbers for the domain. The y, well, you can see here for this particular absolute value, the lowest value you get is 0 and then to infinity. Okay. All right. So 7, 8, 9, 10, and 11. I'm going to open up Desmos and we can play around with some of those. Feel free to do that as well and play around. Put these values in, explore what the square root. Well, we know what the square root looks like. It's this function up here in 4. What happens when I put a negative in front? What happens when I put a negative underneath the radical? You might say, oh, we can't put a negative. Well, the x values would then have to be negative in order to make the radicand, the whole expression underneath there, would have to be positive. So x's have to be negative now. So it flips it around a little bit. And then here we have negatives inside and out. So we'll open those up and play around with a little of those. All right, so now let's go to the last page, the back page, page 2 of our notes on 2.6. So absolute value function in that last problem on the other page is a type of piecewise function, right? So it was look like y equals x on one side and y equals -x on the other side. So it's really a form of a piecewise function. So in other words, how do I figure out, well, I just get rid of the negative, but how do we write that in a real function? So f of x is just equal to x, right? So if I say f of x equals the absolute value of x, this is equal to just the x value when x is positive. It's equal to the negative of it when the x value is less than 0 when it's negative. So when x is positive, the absolute value is just x. And when x is negative, the absolute value is the opposite of that. So that's kind of like the beginnings idea of sort of a piecewise function. All right, so let's look at these. Graph this piecewise function. Note there are sometimes continuous and sometimes discontinuous. All right, so what we got to think about is the domain. So this function is made up of a couple different types of graphs. So we're going to see things like we saw at the first couple of problems, kind of like this. They could be continuous, like this one is continuous, or they could be discontinuous, like this one was in D. All right, so what we got to do is think about what domain we're dealing with. So this first function is going to be graphed now these are the domains, so these are the x values from negative infinity up to 2. So I'm going to just cover up everything else. So we're talking about from negative infinity way over here, the negative infinity for the x values up to the 2, we're going to graph this line. So let's just try graphing that. So it's a line, y-intercept 5, so it's going to be a point here at 5, and then a slope of -2. So I'm going to go down 2, and then to the left one, to the right one, down 2, to the right one again, and we could go up 2 and to the left. So something like maybe up here. Okay, so let's draw that in. So that is this. Now, how do I know to stop there? Because it tells me what the domain for this one is. So let's put an arrow in here that goes on forever in that direction. And then something happens at 2, it flips over. And at 2 now we're going to graph this line from 2 on. All right. Now, we're going to graph that using y-intercept. So that's at 1. And, right, so if we think about this, forgetting about the domain right now, this line goes through the point 1 and has a slope of 1. So we would have it here and here and here and here and here. So if we didn't have a restriction on the domain, we would draw it in like this. However, that line, sorry, I'm missing a couple of the corners there. So we have here, 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 and here. And so I'm sketching this in lightly. But that only pertains to everything above 2, right? So just like the domain here, the domain says 2 to infinity. So we don't want this part of it. That part of the graph, that part of the x values are controlled by this other function here. So ours starts not at 2, but greater than 2. So we're going to have an open circle here. And I sort of have a dot in the middle of that. I don't want that. So open circle, and then the function continues in that direction. All right, and I'm going to emphasize this. This is a closed circle. Which of the two functions controls the value of 2? And you can see 2 is inclusive here, so it's a rectangular bracket. So that's got to be controlled. That function's got to control the 2. So that's a closed circle. The 2 belongs to that line. The x value of 2 does not belong to this line. Does that make sense? And so that's kind of how we do a piecewise function. They're going to have switchover points often at certain values. So here I wrote them in interval notation. Sometimes you see the domains written as just greater than, less than, those kinds of compound inequalities, just as inequalities. All right, so this one now we're going to have 3 different values. So we have x is less than or equal to 0. So that means to the left of the y-axis, this function is going to take control. And so we're up here at 3. Let's draw that in. So we have 3 and a slope of 2. So I'm going to go down 1 over 2, down 2 over 1, down 2 over 1, down 2 over 1. And so that line looks kind of like that with an arrow down here. And then this 0 is controlled by this first function because it's n equals 2. So I'm going to know that that's going to be my solid dot up there at 3. The next one is at 0, it switches over. So now the next function's taking place, but it's only between, let's see if I can show you this, only between 0 and 1. So now we're going to graph the next function, but only between these two regions, only inside here, between 0 up to 1, we're going to graph this thing. So at 0, put a 0 in there, we're at 3, so that happens to be that point. And then at 1, plug in a 1. 1 squared is 1, so that's going to be at 3 minus 1, so 2. So something like that. And so this would be, if we kept going, this would be a parabola, right? And so we would probably put a point down here. So this would be a parabola that would come down and do this, right? But that part of the parabola is we only want that parabola drawn between 0 and 1. And 1 is inclusive, so I'm going to make a closed circle there. And this rest of the graph doesn't exist because now for x values greater than 1, so from here over, we have to graph this thing, okay? And so that's down at -1. So that's like y equals -1. That's a horizontal line down here at -1. So at -1, we're going to draw a line here, a horizontal line. And then what happens here is this function is not controlling the value 1. It was controlled, the x value of 1 is controlled by the second function. So really, let's erase a little bit of that, and let's do an open circle there. All right, so we're drawing the open circle ridiculously large so that you can see them here. We generally don't have to draw them quite so big, but you can see you can't have solids on both of these because then this would not be a function, okay? All right, now the next one. So we have 4 different regions here. So from -1 to 0, so that's in this region, we're going to plot f of x equals from -1 to 0, -1. So that would be down here at -1. It's -1 at the x value of -1. We're controlling it. So it's closed circle goes over here, and then we have an open circle. And then we go to 1, 0, we have 0, and it's controlling this one because it's into the square bracket means it's inclusive of the 0 up to 1, and we're plotting y equals 0. And again, at the far end, 1 isn't being controlled by this function. Instead, 1 is being controlled by the next function. So we do this. So you can see it's like a little staircase that we're drawing here. And then the next one from 2 to 3, inclusive of 2, so we're doing a closed circle there. We're doing y values of 2, so open circle here. Okay, so we have the stair steps function that we get, and that's a type of piecewise function. Okay, so these are all examples of piecewise functions. Notice that we can't have vertical line failing because we're thinking of these as functions. So notice can't have closed circles above each other. Closed circle, anything below it has to be an open circle. All right, so this kind of leads us, this is cumbersome to do this. We have a faster way of doing sort of the step function called the greatest integer function. So it looks like square brackets, but it's a double square bracket on either side of the input or the x. So this function pairs every real number x with the greatest integer less than or equal to. So it's for every value of x, it's the greatest integer that's not actually bigger than that input. So like for example, the greatest integer function of 6.1. So we're looking for the integer, the greatest possible integer that's not itself greater than 6.1. And so that would be 6. All right, so the greatest integer function of 4. So we're looking for the greatest integer that is not itself greater than 4. And so that actually is 4. 4 is not greater than 4. All right, now be careful of this one. It's negative 2.1. So we want the integer that's not greater than negative 2.1. All right, so you might think, oh, it's -2, but reality, no, -3. -2 is bigger than -2.1, so we have to go to -3. It's the biggest integer, not bigger than this. -2 is bigger, right? Think about the number line. So we have -2 here. -2.1 would be to the left of that. So -2, if we said this one was -2, -2 is bigger than -2.1. So we have to go to the other side over here where we have -3. That is the integer. So that kind of confuses people sometimes, but it's -3. Greatest integer function for pi, that would just be positive 3. Greatest integer function of negative 2, though that is negative 2, because negative 2 is not bigger than negative 2. It's actually equal to it. All right. So let's make, so hopefully we won't have to do these kind of tables to come up with these. But for the first couple times, let's do them. And then hopefully you can kind of see a pattern and won't have to always do a table for these. So for number 1 here, the greatest integer function. So the greatest integer function of negative 2.5, it's a lot like this one up here. We saw that's negative 3. And then negative 2, well, that is negative 2. Negative 1.2. That's going to be, again, negative 2. And then negative 1, that's negative 1. So let's stop for a second and plot some of these. Or actually, let's do this. Let's forget about the negatives. Let's just go to the positive ones, and then we'll go back and see how that pattern sort of works. So the greatest integer function of 0, well, that's a 0. So that's, plot that point, 0. 1/2. So an x value of 1/2 now. Greatest integer function of that, still 0. 1 would be bigger than it. And so you can see that this value is just, this graph is going to keep going, keep going. If I had negative 9, it's still 0. Negative 9, negative 0.9999, right? Still 0. Once I go over to 1, then it jumps up. So I'm going to have an open circle here, and it jumps up. And at 1, we're not down here, greatest integer function of 1 is 1. And then I can go over, 1.1, 1.5, 1.9, 1.999, right? All those are going to be 1. And then once I hit 2, an x value of 2, this one's going to pop up. Greatest integer function of 2 is 2. So you can see the pattern that's developing here. And this would just keep going, where we have closed circles on the left, open circles on the right. So you can see that that same pattern would go down here, right? This pattern continues even when we're negative. So we can see here when we are at x value of negative 1/2, that is negative 1, right? And then so this pattern continues. Negative 1.5, that is down here at negative 2, all right? So greatest integer function, just f of x equals greatest integer function of x, looks like this. And we could continue this. If you want, we can just finish putting these in, open. On this side, it's going to be closed, and it goes across. All right, now let's look at what happened. So first of all, too, let's think, if we think about this as a staircase, and we lay a board down on the front of these staircases, notice that that's the identity line. So that line that goes through the front edges, that's y equals x, isn't it? Our identity line. All right, that's not part of the graph, but it just kind of helps you see a pattern there. What happens with that greatest integer function of x. All right, so now let's try some other values. Actually, let's try, let's go ahead and do negative 5/2. And we're plugging it into this more complicated function here. So negative 5/2 times 1/2, that's negative 5/4 plus 1, but let's write that as plus 4/4 so we can add that a little easier. And so this is the greatest integer function of negative 1/4. So the greatest integer function of negative 1/4. And so we know the greatest integer function of negative 1/4. So that would be, negative 5/2. So that's 2.5. We're out here at an x value of negative 5.5. The greatest integer function, then, when we plug that in the expression, we get negative 1/2. So that's going to be down at negative 1/2. That would be down to negative 1. So I know I'm down here at negative 1. Okay. And then let's look at negative 2. So I put negative 2 in here. 1/2 of negative 2, that's negative 1 plus 1. So that's 0. So the greatest integer function of 0 is going to be 0. So we can see how this one's coming over and it pops up there. All right, we're going to see that there's more to this step than what we've done because we just started there, but we'll have to see kind of where this ends up over here, like what this looks like. But let's continue on this direction. So 3/2, so I plug that in. That's going to be negative 3/4 plus 1. So that's going to be 1/4. That greatest integer function of 1/4 is still 0. So we did 3/2. So x value of 3/2, we're still coming over here. Let's try 1. When I put a -1, I mean, when I put a -1 in there, that gives me -1/2 plus that 1. So that's going to be 1/2. Greatest integer function of 1/2, still 0, right? And then let's do -1/2. So that's here. So -1/2, that's -1/4 plus 1. That's 3/4. And that's still 0. So you can see here we're still at 0. The next thing is 0. We put a 0 in, we get 0 plus 1, and that's 1, greatest integer function of 1. So at 0, we no longer down here, it jumps up and does that, okay? So you can kind of see once you establish your step, that pattern is going to continue. So without having to do all of those, notice it would jump up again. And then this one, you can see now we can see, this will go over to here. It'll have a closed circle and continue there. This one will jump up and continue, okay? So also notice, this is interesting, if you just graph y equals 1/2 x plus 1, that sort of seems like the front edge of all these steps, right? A slope of 1/2, y-intercept of 1. So you can kind of see the pattern, you know, kind of helps us so that maybe we won't have to do this stuff as much. You know, once you get one step done, then the rest of them kind of follow suit. All right, and then this last one, just going to do piecewise. So here, up here on 4, 5, and 6, they gave us the piecewise function, asked us to graph it. Now we're sort of giving you the function again with its related domain and asking for particular values. So f of -4. So I'm going to plug in, you know, that -4 into my function, but which one of these do I plug it into? Well, I have to look and see where this x value of -4 is. Is it in this domain, this part of the domain, or this part of the domain? So clearly it's in this first part of this domain. It's between -infinity and -2. And so I'm going to plug -4 into this function. I'm not going to plug it into all of them. I'm just going to plug it into the one where this x value falls into the domain. And so it's definitely that first domain. And so I plug this in, I get -4 squared, which is 16. So I get 16 minus 2. 16 minus 2 is 14. All right, so f of -4 is 14. All right, so now let's try f of 0. Where does 0 fall in? Which of these domains does our x value fall into? This time it falls into this one. So I'm going to put 0 as an x value into this x here, into the second function. So that's going to be 3 minus 4. So this is -4. Okay. Let's try b. Sorry, I was going down. b is across. So what is f of -2? All right, so does that fit into this function or to this one? And I think you can see that it's fitting into this one. -2 is up here. -2 is not inclusive here, but it is inclusive here. So I would say for b, I would say with this same function. So we put -2 squared, that's 4, minus 2, that sounds like 2. All right, and then d, we have 5. So 5, I see it here and I see it here. Which domain am I going to put that into? Which domain portion does 5 fit into? And it's this bottom one because it's inclusive of 5 here. It's exclusive of 5 up here. So I'm going to put 5 into this function, and I get what? 10 minus 25, so -15. -15. Sorry, I lost my negative there. -15, 10 minus 25. All right, and then this one here, f of 10, where am I plugging that into? Kind of looks like it fits into this domain, 10. So I'm going to do 100 minus, 10 minus 100. And so that looks like -90, okay? All right, so the homework in this section is here. You'll definitely probably want some graph paper in order to do some of these. Some of them you're definitely going to be graphing them.